In this video, we will introduce our work MPIB, an MPI-based bokeh rendering framework for realistic partial occlusion effects. Our work focuses on a common phenomenon in bokeh rendering. That is, partial occlusion effects. This phenomenon denotes that when the background is refocused on during the rendering, blurry objects near a camera become semi-transparent, resulting in partial appearance of the occluded background. Existing rendering methods, no matter physically based ones or neural ones, have difficulty rendering realistic partial occlusion effects, especially when the texture of the background is complicated. Inspired by the multiplane image representation, which is firstly proposed for novel view synthesis, we introduce a new rendering framework, termed MPIB. This framework first combines an MPI representation module with a background in painting module to obtain a high-resolution 3D scene representation. Once the scene representation is obtained, it can be reused to create different bokeh effects with different controlling parameters. The well-known MPI representation consists of a set of frontoparallel planes. Each plane encodes an RGB image and an alpha map. In novel view synthesis, one can reconstruct the scene by continuously using the alpha compositing operation to MPI planes with a back-to-front order. When applying this formula to bokeh rendering, we blur each layer with a fixed-size kernel, which is adaptive to controlling parameters. Furthermore, we add weight normalization to alleviate the artifacts caused by discretization. In background in painting module, we combine an off-the-shelf in painting model with an occlusion mask generator to produce a background image. Since occlusion often occurs where the disparity of the scene changes significantly and the occluded area is on the side with a larger disparity, we design an occluded mask generator according to this principle. In MPI representation module, we first propose MPI-net to obtain an initial MPI representation. For each image, the encoder runs only once, while the decoder runs multiple times to generate different planes. To reduce the difficulty of training MPI-net, we assume that the RGB image of each plane is the per pixel weighted average of the original all-in-focus image and the in-painted background image. As a result, for each plane, MPI-net only needs to predict an alpha map and a blend weight map. To adapt our model to high-resolution input, we also propose AUP-net, a lightweight upsampling network, to iteratively upsample the alpha map guided by the high-resolution all-in-focus image and disparity map. To obtain ground truth bokeh images, we design a ray tracing-based bokeh generator. Given a background RGB image and two foreground RGBA images, we first construct a 3D scene through randomly setting the positions and disparities of different objects. Then, we can easily synthesize an all-in-focus image and a corresponding disparity map, and produce a bokeh image by our bokeh generator. Specifically, we first set the disparity of each object to a plane function. For each pixel, we sample multiple rays and calculate the intersection of each ray and the scene. The final rendered result of the processed pixel is the average colors of all intersections. In experiment, we first evaluate our method on a synthetic dataset, which is produced by our ray tracing-based bokeh generator. The results show that our approach outperforms other methods both numerically and visually. Then, we conduct a user study on real-world images, where the disparity maps are predicted by a monocular method. In addition, for each image, we set two focal points, one on the foreground, and the other on the background. The experiments of these two types are counted separately. From the results, our approach is most favored no matter the image is refocused on foreground or background. We also compare our approach with iPhone 13 cinematic mode. One can see that our approach supports larger blur amounts and creates much more realistic partial occlusion effects. Finally, we show some synthesized animations with different controlling parameters, including blur amounts, refocus disparities, and gamma values. For more details, please visit our website. Thank you for watching.